All right, in this video, we are going to be starting the continuity notes. So far this unit, we've talked about a lot about limits involving infinity, limits being solved with direct substitution, solving algebraically, solving given a graph. So let's talk about continuity of functions. So first off, at the top of your continuity notes, it says a function is continuous if you draw the function without ever lifting your pencil. The following graphs demonstrate three types of discontinuous graphs. All right, so surely you talked about this at pre-calc and maybe before that, but let's review the three main types of discontinuity. We've got the first one is a removable discontinuity. It's the only removable discontinuity. That's where we have a hole. The other two are non-removable. We've got a vertical asymptote, which is also called an infinite discontinuity. And then we have a jump discontinuity that we see oftentimes in piecewise functions or step functions, things like that. All right, it says there are two types of discontinuities, removable and non-removable. A hole in the graph is an example of a removable. It's considered removable because you can easily make the graph continuous again by filling the hole. And we'll look at examples of doing that later on. Vertical asymptotes and jumps are examples of non-removable discontinuities. They cannot be made continuous. All right, so let's look at example one. I've already got these filled out for time's sake. We've got this graph here of a piecewise function. And the directions say find the points and intervals at which the function below is continuous and the points at which it is discontinuous over the interval from 0 to 5. All right, so it looks like we've got three main pieces here. This hole right here at x equals 1. All right, so regardless of the fact that it's got a discrete point up here, that's a hole, so removable discontinuity at x equals 1. Let's start there. If we keep tracking our domain to the right, these two pieces that look like they're increasing without bounds show that there's a vertical asymptote here, which is going to be that vertical asymptote or infinite discontinuity, and that's at x equals 2. And those are always non-removable. And then if we keep tracking to the right, then we follow this curve past 3 up to 4, and then we've got a jump discontinuity between the second and third piece at x equals 4. So non-removable jump discontinuity at x equals 4. All right, so those are the discontinuities. So then it also asks for the intervals where it is continuous. So if we go from 0 to which is the beginning of our domain, to 1, our first discontinuity, there's that first piece. Because it's discontinuous at 1, we want to continue to use parentheses and not square brackets. So these are intervals, not coordinate pairs. And then from 1 to 2, between the hole and the vertical asymptote, and then from 2 to 4, it's continuous. Even though they show a point right here at x equals 3, there's no hole there, there's no discontinuity. It looks just like a local minimum. And then on the other side of that jump discontinuity to the end of our domain from 4 to 5. All right, so those are the continuous intervals. All right, so let's look at a calculus-based definition of continuity at a point. It says a function y equals f of x is continuous at point C. The limit as x approaches C of our function equals the function evaluated at that C value, okay, f of C. In other words, if the left-sided limit as x approaches C of the function equals the right-sided limit as x approaches C of the function equals that actual y value of the function there at C, then it is continuous at that point. So this is the second part that I've highlighted is going to be what we're going to use to prove whether a function is continuous or not at a given point. All right, that's why I highlighted that part. Okay, you should too in your notes. Let's look at example 2 on the next page. It says for C equals 1, 2, and 4, so they give us three different x values. Find f of C, the right-sided limit, the left-sided limit, and the two-sided limit at each of those C values. Take notice how each part of the definition of continuity is important. So I might be flipping back and forth between the definition and here. So this looks like the same graph that we had before. So if we start off by letting C equal 1, then it says, all right, let's find our left and right-sided limits going towards 1. So if we track our graph, so we approach 1, it looks like it's approaching a y value of 1. Okay, from the right, from bigger values of 1, as we approach 1, again, the height is approaching positive 1. So the two-sided limit is 1. So if we evaluate f at 1, unfortunately, because of this point up here, this discrete point at 1, 3, f of 1 is not the same as the limit as our function approaches 1. All right, so we show that they're not the same. Therefore, f of x is not continuous. Right, so we know by looking at the graph that it's not continuous because there's a hole there. But we want to do just more than just say there's a hole there. We want to be able to prove it using the definition of continuity. This is something that's going to come up over and over again in calculus, to where we need to justify a statement that we make, and we're going to need to justify it with a theorem, with a definition, or just with showing step-by-step, kind of explicitly laying it out clearly, that it meets certain requirements for it to be, or in this case, not to be, what we're asked about, which in this case is continuity. All right, for c equals 2, all right, that's where our vertical asymptote was. Also approaching positive infinity, but at f of 2, that function is not defined. There's no values that we can get an output for at 2, undefined. Even though you could technically say the two-sided limit doesn't exist, they're not the same value, and so not continuous at x equals 2. Again, we know that looking at the graph, because there's a vertical asymptote. We just went over the different discontinuities, but we're proving it by the definition of continuity. Lastly, let c equals 4. So now we're looking at this jump discontinuity here. So again, left-sided limit, we're looking at a y value of 2. Right-sided limit, we're on this last piece here, approaching 4, which approaches a y value of 1. Those two-sided limits are not the same, so it actually doesn't even matter where it's evaluated. 2 doesn't equal 1, so by the definition, we've proved that it's not continuous at x equals 4. Okay, showing each of those steps is important. All right, you don't always get a picture, so you have to be able to do this algebraically as well. Example 3 says, determine whether each function is continuous or not. If it is not continuous, use the definition of continuity to explain why. All right, I'm going to go kind of quickly through these because I think I'm running out of time. 2 minutes left. All right. Okay, f of x equals 1 over x minus 1. Simple rational function shifted to the right 1. Set that denominator equal to 0. We've got a vertical asymptote at x equals 1. Okay, we want to, we already know there's a discontinuity there, but using the definition, we need to show left and right-sided limits, which, again, imagine values getting closer and closer to 1 from the left. We can use our signs, knowing that it's going to be either positive or negative infinity because it's a vertical asymptote. And we get left side is negative infinity, but the plus side is positive infinity. It's not going to be defined at 1 anyways, so they are not equivalent. Therefore, it is discontinuous at x equals 1. Part B, g of x, another rational function, factor it. You're going to find common factors in the top and the bottom, which will cross out, which leads you to a hole. Set that x plus 2 factor equal to 0. You get your hole at x equals negative 2. So that's where we're investigating. Left-sided limit, right-sided limit. You could just do direct substitution into the leftover 2x minus 3 function, and you're going to get negative 7. But the function is undefined there. Negative 7 doesn't equal undefined, so it is discontinuous at x equals negative 2. All right, lastly for part C, h of x. Got a piecewise function. Left piece is linear, right piece is a quadratic. The left-sided limit is going to use this linear rule that is stated for x values less than 1. Find that left-sided limit. You get a value of 1 by doing direct substitution. Right-sided limit is going to give you your limit coming from the right of 1. Plug it in, we get 1. Those two line up, evaluate it at h of 1, which is using this quadratic piece again. We get 1 again, so 1 equals 1 equals 1. Therefore, h of x is continuous. Linear is continuous. Quadratic is continuous, all the other parts. So that's a continuous function.